now we make use of the Amperes Law to derive some simple equation. So yesterday we actually derived this one using the Biot-Savart law, and actually this Amperes Law is of course compatible to the Biot-Savart law. And which means that they can actually derive the same equation for this case. And yeah, so in chapter 23 we also do similar things. It tells you that the Coulomb's law is compatible to the Gauss law, if you still remember. Actually, we can use simply apply the Gauss law to derive the Coulomb's force. So actually, we use this Amperes law to really derive this one. So actually, when you consider the current here, we have a current here going out of the page. Now we actually this whole blue circle is the cross section of the wire. We only make this dot here. It doesn't really mean that the current only at this point, actually at the whole wire. But actually the whole blue area, the cross section of the wire. So in this case, we define the Amperes loop with this red circle counterclockwise. So in this case, this current is a positive current. So so for part one, if we apply the Amperes law, on the left hand side we have the line integral. If we have the line integral, and as much as this one is symmetric, we already know that the B field should be parallel to ds. Suppose this is a perfect circle, which means that when we connect a line here, then it should be perpendicular to this line. Because the ds is tangent to the circle. And also the B field should also be perpendicular to this line. So they should be parallel to each other and point to the same direction, which means that this B dot ds should be nothing but a B times 2 pi r. Similar to when we applying E dot dA. If E is uniform over the Gaussian surface, it will be like E times A. So now, as much as B is uniform over this circle, they will always parallel to ds. And so now we just multiply B by the total length of this circle. So it is B times 2 pi r on the left side. So on the right side, it is mu0 I enclosed, and in this case we have I to be our I enclosed. So we simply can get B equals mu0 I over 2 pi r. So this is really important, as I mentioned yesterday. So next, we have another case. This is the other case. So for this case, we add another condition is we consider the magnetic field out of the straight wire, which means the blue area is the straight wire, and now we consider the B field out of the wire. But if we consider the point inside the strict wire, then it will be different. It will be different. So here, if we assume, if we assume this is the wire, and now we define the Amperes loop. This is the Amperes loop. This is the Amperes loop, and going counterclockwise, similarly, and the total current is I, and assume the current is uniformly distributed, I over the whole wire. So, so when we consider the I enclosed, we can only count the inside part, but not the outer part. So in this case, we will have, let me see. So we will have I, I over. So we'll assume the radius of the wire to be capital R, and the radius of the Amperes loop will be small r, similar to this case. So you need to distinguish the small r and capital R. So here, I is over pi capital R squared. So the total I over the total cross-section area of the wire will be the density, and we assume the current density to be uniform, which means that I enclosed is actually pi R squared, which is the enclosed area. So in this case, pi and pi will be cancelled, so we will have I enclosed to be I times small r squared over capital R squared. So similarly, we apply the Amperes law on the left side. It will be the same because it's still symmetric. So B times 2 pi R on the left side, and on the right side we will have mu 0 I enclosed. Now we have mu 0 I small r squared over capital R squared. So in this case, this small r and this one of the small r will be cancelled. So finally, B will be mu 0 I small r over 2 pi capital R squared, which is this one. So this is a very simple derivation for the B field inside and out of the wire if we assume the current density to be uniform. So we know that for that case it is a little bit different. For this case, we assume that this wire is very thin. It's infinitely thin. There is no thickness. There is the radius will be zero. For this case. This is a thin, infinitely long wire. So we get this result. However, if we assume this wire to have a radius of a capital R, so as much as you consider a point out of this wire, then you can still use this same expression to find the magnetic field magnitude. However, if you consider the magnetic field inside the wire, then it is different. Similar to when we consider a sphere. If we have a sphere with some charge with some charge, and then it distributes uniformly, and then you consider the E field out of the sphere and consider the E field inside the sphere, then when you consider the E field out of the sphere, it will be proportional to 1/r squared. And if you consider the E field inside the sphere, then E will be proportional to small r. So quite similar, but not actually the same. Not actually the same. So here inside the wire is proportional to r, and if it is out of the wire, then it is inverse proportional to r. Any questions? Okay, now we consider a sample problem. So here the cross-section of a long conducting cylinder with inner radius small a and outer radius small b. So the cylinder carries a current out of the page, and the magnitude of the current density in the cross-section is given by J equals CR squared, with C to be this value. What is the magnetic field B at a point that is 3 cm from the central axis of the cylinder? So small a is 2 cm, B is 4 cm. Now we consider the point at 3 cm away from the central axis, which means we consider the B field inside this part. Of course, we cannot apply this one directly because this wire is hollow, so we don't have a current in the middle part. Okay, so now, of course, we have a J or I. We have J to be out of the page. Maybe we can mark it here so that we will be able to know that so the current is going out of the page, and maybe it intentionally define the Amperes loop to be clockwise. And as you know, if we define this loop to be clockwise, then the positive direction should be into the page. So in this case, this current is a negative current. So in this case, so first we consider the I enclosed. The I enclosed is actually this part. We consider this part. If we really need to consider the B field at this point, then we will integrate the whole wire, the whole hollow wire. But however, we consider the B field at this point, so we only integrate up to R equals 3 centimeters. So now I enclosed should be J dot dA, and so as much as this loop is clockwise, so in this case we will have our dA into the page, so positive direction. And also, counterclockwise is the positive direction for the B field. So now we should have J to be parallel to dA. So dA also pointing into the page. also pointing into the page. So in this case, J and dA should be parallel to each other. So we have minus J is CR squared. So we have CR squared. And then of course we know dA for the polar coordinate should be R dr d theta. R dr d theta. So we have R dr d theta. Oh, maybe I should leave some space here because it should be actually a double integral. So it should integrate out from A to let me see, R, small r. Or maybe I should put it R prime here because this is a dummy variable. It will be conflict with this one. So we have R equals 3 centimeters. And theta, which is the whole circle, so we integrate theta from 0 to 2 pi. So now we have minus C, and then totally we have R prime cubed. So R prime cubed, and then dr prime from A to R, and then d theta is from 0 to 2 pi. So in this case, we have R to the 4th power over 4 for this antiderivative. So we have Z R prime to the 4th power over 4, and then we evaluate at R and A, and then subtract them. And still we have this one. This one, the integration will be theta, and then evaluate at 2 pi and 0, so it will be 2 pi. So finally we have a minus C, and then R to the 4th power minus A to the 4th power all over 4 times 2 pi, which is minus C prime over 2 times R to the 4th power minus A to the 4th power. So we can plug in all the values. So we have a C is this one, minus 3 times 10 to the 6th power, and then times pi over 2, and then R is 3 centimeters, which is 0.03 to the 4th power, minus A is 2 centimeters, which is 0 times 0.02 to the 4th power. So finally, this value will be let me see, well, maybe we stop here first. I don't really calculate the number here. Okay, so maybe we just hold up to here. We don't need to plug in all the value yet. So now we can apply the let me see. So we can just keep this one, maybe. So we can keep this one here, and then we should have B dot ds equals mu naught I enclosed, and we already know that I enclosed is minus pi over 2c times r to the 4th power minus a to the 4th power. So we have this one so far, and on the left side it will be nothing but a 2 pi r times b, similar to the previous case, because it is still symmetric, and then all the b field parallel to the ds, and yeah. So we have 2 pi rb on the left side, and then it should be mu0, and then we plug in I enclosed, which will be minus pi over 2c, and then times r to the 4th power minus a to the 4th power. So finally, b will be pi and pi will be cancelled, and then it will be mu naught minus mu naught c times r to the 4th power minus a to the 4th power over 4 pi. So now we can plug in the values. So you know mu naught is 4 pi times 10 to minus 7. So together with this 4 pi, we have a minus 10 to the minus 7. And then times c will be these are 3 times 10 to the 6th power times 3 times 10 to the 6th power, and then 0.03 to the 4th power minus 0.02 to the 4th power. And then so the final value should be oh, I skip an R here. Here we should have an R. So all over 0.03. Sorry, the pi already cancelled, so it should be 4R here. So we still have pi times 10 to the 4th power. Yeah, the pi already cancelled. So we have pi times 10 to the minus 7 here. Minus pi times 10 to the minus 7. Should be like this. And then, so you can use calculator to find that this is minus 20 mil Tesla. 20 mil Tesla. So actually, as much as we define this is the loop direction, and we find that b is a negative value, so that b is counterclockwise. As b is a negative. B is negative. And then the loop is defined clockwise. If it is a positive number, then b is clockwise. If b is negative, then b is counterclockwise, according to this one. And of course, this direction, which is a dA direction, and also the direction of the current, will also depends on this definition of the loop. So as much as you follow all the polarity, then you will get the correct answer. Actually, if you define the loop in a clockwise way, so if you really define the loop so now if you define the loop in counterclockwise way, then you have the current to be a positive value, and finally you will get a positive number, which means that you will still get the B field to be the same value, but 20 mu t, and B is still counterclockwise. It doesn't really matter how you define the loop direction. You define the other way, either way, and still you can get the correct answer. I think this sample example intentionally try to define the loop in the opposite way to the current direction, so that it tells you that even though you still you define the loop direction in a so-called incorrect way, then you still get the correct answer. Any questions? Okay, so next we talk about the solenoids. Yeah. So here we have the magnetic field of a solenoid. So actually it's nothing but this one. This is a solenoid. So the current will be going like this, and yeah, actually it will generate magnetic field. As you know, it will generate magnetic field, because if there is a one loop, then it will generate the B field. At the center, you can actually know the value, which will be mu0 I over 2R. Of course, no pi there, because mu0 I over 2 pi R is for a straight wire with a radius out. But for this one, if this is the current loop, and at the center, the B field will be B equals to mu0 I over 2R. mu0 I over 2R. This is R. And of course, if we have many loops or many turns, then all the B field will be add together, because actually all the current direction of the loops will be the same, because it's actually a loop. So the solenoid magnetic field is the vector sum of the field produced by the individual turns, or call it windings, that make up the solenoid. So for the points very close to a turn, the wire behaves magnetically almost like a long straight wire. So we try to zoom in to the solenoid. So for this figure, we try to zoom into this solenoid. So there will be a large gap between them. So actually, if you consider the area inside this loop slightly far away from the wire itself, then it will like the uniform B field there, pointing this way. And actually you can use the right hand rule to determine this direction, because here we should have here you can see this is into the page, this is out of the page, which means the current is going in this direction. Like from top to bottom, this way. So you can use your forefinger, follow the direction of the current, and then your thumb will point to the right side. So by right hand rule, then you can know that this is the direction of the B field. So it's kind of follow this one. So consider within this area, it is kind of uniform inside. Of course, there will be some fringe B field out of this solenoid. However, we mainly consider the B field at this area, So the wire behaves magnetically almost like a long straight wire at the line and almost a concentric circle. So the field tends to cancel between adjacent turn, tends to cancel for the adjacent turn, which means that if you consider this turn and this turn, so at this area, in this at this point, so if you consider the point here, then for the left wire, it will have magnetic field like this. You have magnetic field like this. So if you consider the area close to the wire, then it will not be that case, and you use the right hand rule, and then your thumb follows the direction of the current. Your thumb points to the direction of the current, and then the other four fingers will be the direction. Forefinger will follow the direction of the B field. So now you can see the direction is like this, roughly counterclockwise at this cross section, and likewise for this one, the B field is also counterclockwise. So at this point, this one pointing upward, this point pointing downward. So in the middle point, they will be kind of cancelled. Of course, not exactly. If it is not exactly at the middle point, then the B field cannot be perfectly cancelled. So, but however, the B field would be cancelled by a portion, depends on the point there. But such you can know for the concept of the magnetic field line. If the line are not so dense, then you can imagine this part is has a weaker magnitude for the B field. So if it is close to the wire, then the magnetic field will be weaker. So for this part, it has a stronger magnitude of the B field. So this is the field tends to cancel between adjacent turns. And a point inside the solenoid and reasonably far away from the wire, it is approximately parallel to the solenoid. So just now I mentioned, so if it is inside the solenoid and parallel to the central, then yeah, the B field is parallel to the central. So this is so-called the solenoid, and yeah, actually you will, yeah, even though you will not need to calculate oftenly, but actually all of you should have one on your hand. Actually, if you consider your smartphone, for the antenna, it is actually some sort of a solenoid. I have made a video in my YouTube channel a few years ago. Then actually it tells you that at that time usually the smartphone case can be open. Now usually it cannot be open, and actually the antenna is designed on your smartphone case. Yeah, so there will be many loops for different signals. Maybe one for the Wi-Fi signal, one for the 2G, 3G, and maybe one for even 4G or 5G, and one for GPS. Then if you just remove the case, then the signal strength your mobile phone receive will be significantly decreased. So actually, it depends on the magnetic field and the electric field, the EM field. So maybe in the next chapter for the magnetic induction, it will be more related to the antenna. And of course, we will still talk about the EM field in chapter 33. Okay. So maybe this derivation is long.